Thank you for the introduction. My name is Liu from the University of Chicago. So this is joint work with my colleagues Amanda, Max, David, and Blaise. So in this work, we introduce new techniques for reasoning scientifically about password cracking software. But wait a minute, why are we even talking about passwords here? I know many people say that passwords are dead, but here we are still living in a world of passwords. Imagine a password, Chick4Go. Is this a good password? Will it survive an attack? So one type of attacks we need to worry about is offline guessing, where the hackers trying to crack a hashed password or a password protected file. So what they would do is they'll make a guess, hash it, and check their guess. For example, they'll guess 1, 2, 3, 4, 5, 6, and compare these two things. And they'll keep doing this until there's a match. So now they know the password is Chick4Go. So ultimately, what we care about here is I have a password. Will it be cracked or not? But this is a complicated question. It depends on all the assumptions you're making here, from the attacker's motivation to the hardware you assume to have access to. So a common abstraction we did here is that we model a plausible attack. And you count how many other things are guessed before guessing this password of interest. That is, we are turning this password into a guess number. In this toy example, the guess number is 6. But in a real attack, the guess number might be something like 13 billion. And if this guess number is large, many other things are guessed before this password. So the password is probably strong. And if the number is small, it means the password is likely to be weak. And since we're modeling an attack here, it raises the question of how passwords are guessed. So how are they guessed? The first thing you would do, so the best source for guessing a password is hard passwords. And nowadays, more than billions of passwords are leaked. So the first thing you would do is you will sort them by descending frequency and try them. But the out of guesses quickly, because on modern machines, you can make billions of guesses per second for fast hashes. So what if you haven't guessed a password? What's next? So this is where the password cracking methods come in. And there are two words of password cracking methods. On the one side are the probabilistic models that we as researchers use. On the other side are the software tools like JonDarryP and Hashit. These are the tools used by InfoSec professionals and the real-world hackers. So given cracking method, how do we get the guess number? The community already knows how to compute a guess number for the probabilistic models. So this work will focus on getting the guess number for the software tools on the right side. So how do you do this? How did you get the guess number? The naive way to do this is you run the algorithm, you're generating guesses, and you stop when the target appears. This is fine if you only have 6 guesses. What if you need to make a quadrillion guesses, which is 10 to the 15 guesses? What if you need to make 10 to 20 guesses, and the password is at the end? So the problem here is that this approach does not scale. So this leads to our analysis goals of getting the guess count for software tools. So first, we want the process to be efficient. And second, as I'll tell you later, the software tools require some detailed configuration. So we want a systematic and scientific process for configuring these tools. And first, I'll introduce what is the state of the art. For the probabilistic models that we as researchers use, there's a fast way to get a guess number. A paper at CCS 2015 introduced using Monte Carlo methods to estimate a guess number without running the algorithm. So we can get guess number efficiently. And of course, the guess number depends on the configuration. But this is somehow already built in. For these probabilistic models, given some training data, they mostly config themselves. So everything's fine for these models. And they have some good properties. So first, they guess efficient. But their walk-up time is slow. And this is why real-world hackers are not using these algorithms. So what do hackers use? The password cracking community has developed software tools like Jungle Reaper and Hashcat. And instead of trying to generate some probabilistic models, they try to perturb words in the way that a human does when creating a password. So humans might take a password, take a word, append some digits, make some character substitutions, or switch cases. And this is the inside. And for a word like Chicago, you might want to generate all the variances listed here because they're generated in a way that human does. So this is the insight behind these tools. And these tools are less gas efficient, but they walk on time fast. They can generate much more gases per second. So you can think of the hackers as they're shooting with a machine gun, that they try to win with quantity over quality. And here comes the question again. Here's my password. Tell me the guess number. Well, prior to our work, you have to do this the naive way, enumeration. But this is not going to work, because usually when you're typing a password and you want to know the guess number immediately. But with enumeration, at best, you will say, come back tomorrow, and I'll let you know. And this expensive enumeration also makes configuration hard. Because every time you try a new configuration, you have to wait hours to see how good it is. And this leads to our work. We introduce new tools to reason scientifically about real-world password cracking software to address these two issues. But before I dive into our work, let me explain how these tools work. So the most common attack performed by these tools is what we call a mangled word list attack. It takes in two types of inputs. The first, a word list, which consists of common passwords or any words that you think are good as starting points. Because the idea is to perturb words in a way that human does, it takes in a rule list that specifies how to perturb words. And the tool will now issue a stream of guesses. You will first append 1 to super and guess super 1, and then append 1 to password and guess password 1, and append 1 to Chicago and guess Chicago 1, and then move to the second rule, apply it to everything in the word list. And you keep doing this until you're out of words and rules. So what do word lists and rule lists look like in practice? A word list might have 20 million words or 500 million words, while a rule list could have 5,000 rules or 65,000 rules. And with a typical configuration like this, you'll get something from billions of guesses, trillions of guesses, to quadrillions of guesses. But the lists here are just we as researchers use. Evidence has shown that hackers have their private word lists and rule lists that are likely to be much better than what we have. And right now, without investing huge resources, it's impossible for the researchers to catch up with the list hackers have. Unfortunately, we make it possible. And now I'm going to tell you how we do this. So first, I'd like to show you how we estimate the guess number efficiently. So the first thing you want to know is whether this password is correct or not. And normally, you do this in the forward direction, which of course requires enumeration. And as we've established, this is not going to work. So inside here is we can go backwards. Suppose you have a password, Chick4Go, and we wonder, will this password be guessed by the first rule? Well, obviously, it cannot be guessed by the first rule because Chick4Go does not end with a 1. And now we wonder, is Chick4Go will be guessed by the second rule? Well, likely. So what words should be in the word list to guess Chick4Go? And we term these words preimages. And turns out, in this example, there are two possible preimages. And either of these preimages will be transformed into the password after you apply the second rule. And this actually saves you a lot of time. Because if you do it in the forward direction, you'll make millions or billions of guesses. But here, we just need to do two lookups in the word list to say, if is Chicago in the word list? Is Chick4Go in the word list? But things are not always this easy. Jungle Reaper and Hashcat supports more than 65 different types of transformation. Some of them pretty easy, like append a digit. Some of them are very complex, like purge all digits. And you can even use rejection clauses to filter unwanted guesses. And what's even worse is that you can compose different transformations into one rule. And this is a real rule from Hashcat. What it does is that switch the first and sixth character, and then delete the first three characters, and next, duplicate the whole word, and finally truncate the word to length 7. And now I have a password. Can you tell me what the previews are? Well, our tool knows. And in fact, we're able to support the majority, but not all of the transformation. And we can deal with arbitrary composition. So what we did is that we introduced some intermediate data structure to represent the results efficiently. And next, now we know which word and which rule would guess the password. But we also have to know how many other things are guessed before our target. Suppose we know how many guesses are made by each rule, we can quickly bound this number. And in this example, the guess number is between 4 and 6. But we also know that Chicago is the word that cracks the password. So we can use Chicago's position in the word list to estimate the guess number within the bound. But in reality, it's often non-trivial to get the number of guesses made by each rule. So a major complication is when rejections are used. For example, here we say skip this guess if the word does not have an A. Otherwise, replace it with 4. So we have to reason about how many words have an A. And this gets even more complicated because the rejections could appear anywhere in the rule. And this will introduce very complex dependencies. And as usual, we're able to handle most, but not all of the transformations, and can deal with arbitrary composition. What we did here is that we represent the dependencies as tensors and make one pass over the rules, over the word list. And now you can count how many guesses are made by each rule efficiently. So with these new tools, we enabled fast guess number estimation. We benchmarked our performance on real data. We used the LinkedIn password dump as our word list and a rule list called Spider Lab. Together, they will issue 3 times 10 to the 14 guesses. And if you enumerate everything once and save it to disk, it will take you 3 petabytes of data. Well, we only need 10 gigs of space. And piping everything to disk will take you more than 2 years. And of course, this is I/O bounded. Well, we just need less than a day to do some pre-processing. And after the one-time pre-processing, we estimate the guess number in less than a second. We don't know the lookup time for the naive approach because we didn't pipe 3 petabytes to our disk. And now it comes to our second goal. We want to be able to reason about different configurations and potentially identify the best one. So the configuration of these tools is just the word list and the rule list. More specifically, the performance of these tools depends on the order of the rules, as well as what these rules are. It also depends on the order of the words and what these words are. And our insight here is to use data, for example, leaked password sets, to improve the configuration. Using this password as training data, we determine the new configuration. In the interest of time, I'm just going to cover how we order rules and how we improve the contents of the word list. So the first question we ask here is, should the rules be in a different order? And our key idea is to order the rules by guessing efficiency. Basically, we order them by the number of cracks per guess from high to low. For example, let's look at the Spider Lab rule list, which was manually ordered by some human expert. And let's plot the let's plot the percentage of password crack on the y-axis versus the total number of guesses made on the x-axis. For a particular password set, here's how the guessing curve would look like with the rules in their original order. And now suppose you know everything in the test set and reorder the rules. So basically, what we're doing here is we train and test on the same test set. So you will get somehow an ideal order of the rules. And what should that curve look like? So you'll get something like the red dotted line here. And instead, we train the order on some other test sets. So basically, we're testing on one set and training on the other set. And we can see here, the data-driven approach is nearly as good as the optimal you could get. And this shows the power of data-driven configuration. And we're also interested in what other words should be in the word list. And our insight here is we should add the preimages that are missing in the word list. Recall that we're looking for preimages in the word list. So what if a preimage appears a lot, but it's not in the word list? This is like cache misuse, and we should probably add it to the word list. And we rank these preimages by frequency. And we're able to identify 3 types of missing preimages. The first is site-specific. Our results suggest that to attack passwords from Battlefield heroes, you should add words like BF heroes. Of course, it's not generalizable, but this actually sanity checks that our approach makes sense. And we also identified generalizable words like master brain. If a master brain could have cracked passwords in one set, you might help crack passwords in another set. And this was actually the case. And finally, we identified short strings that crack passwords in multiple test sets. This is interesting because when someone is constructing a word list, they use common passwords or words from dictionaries. But they're really taking into consideration of the rules they use. And these short strings, when paired with some rules, are actually very helpful. And to wrap up, we introduce some of the first analytical tools for reasoning scientifically about real-world password cracking software. And built on top of these tools, we enabled fast guess number estimation. We also built configuration tools for word lists and rule lists. And we also open source our code on GitHub, so feel free to play with it. And from now, I'm happy to take any questions. Thank you.
We have some time for questions. If you have a question, please do come up to the mic.
Hello, thank you. Very nice talk. Very nice work. I'm Rahul from Cornell. So I have one question. The rule set that is used by John the Ripper, aren't they fall in any regular language categories, like regular languages or PCFGs, so that we can like quickly use the techniques tools from there to estimate the guess number?
Sorry, can you repeat your question?
Yeah,
again?
sure.
I didn't get the last part.
I'm saying like, does the rules that are used by John the Ripper, they don't fall any standard categories like regular languages or PCFG?
Oh, the rules are actually specifies how to transform the words. So I guess they don't fall into languages.
Like it's like a transformation rule. So you take an input as one word, and then you apply a set of transformations, which can be represented as a state machine. So I'm just asking, is it any standard set machine? Like, aren't there regular languages?
Sorry, I don't think I get your question.
All right.
But I'm happy to talk about it.
Yeah. Thank you.
Hi, Scott Rudy from the University of Tennessee. So really cool work, especially if you're an adversary. You've given them a nice, new, powerful tool. So from the perspective of the defender, though, it feels like the reduction in the guess estimates that you're giving, while more accurate, are still within the kind of that uncanny valley between offline guessable and online guessable. So how does this information effectively help defenders?
OK, very interesting question. So I think one thing we mentioned in my talk is that the attackers actually have invested huge resources to their word list and rule list. So they probably already get something that's nearly optimal. So we do help the attackers a little bit, but they're already there. What we did most is like we helped the researchers to quickly catch up with what the attackers have. And
how does catching up help us do better? Is my question.
Oh, how does catching up makes it better? So basically, we want to model what's in, I guess, what real world attack is, and this is the real world attack. So we want to understand what would do, right, with their, I guess, word list and rule list. So this gives us a sense of what they might, like what attacks you might under attack in I guess, real scenarios.
Okay, thanks.
Thanks.
All right, let's thank Alex again.